Have you ever stopped, perhaps late at night when the world grows quiet, and asked yourself a deceptively simple question? Why does the universe feel so close in our imagination, yet so impossibly far in reality? You see, we look up and the stars seem almost within reach, tiny pinpricks of light scattered across the sky, and yet each one is separated from us by distances so vast they mock the length of a human life. Well, the nearest star beyond our sun is so far away that its light takes more than 4 years just to arrive here. And that's the thing, even light, the fastest traveler the universe allows, moves at a pace that turns interstellar dreams into generational epics. And when you think about our spacecraft, brave machines built with extraordinary care, you realize they crawl through the cosmos like ants crossing a continent. Voyager has been traveling for decades and still has not truly escaped the sun's influence, so I suppose the universe feels a bit like a prison built not with walls, but with speed itself. And that raises a deeply unsettling and quietly thrilling question. If we cannot run faster, if every engine we build only pushes us deeper into the same limitations, then perhaps we are asking the wrong question entirely. Perhaps the real mystery is not how to move faster through space, but how to persuade space itself to move, to bend, to flow around us. You know, Einstein taught us that space is not a rigid stage. It is elastic, responsive, alive in a sense. And in the early universe, it expanded faster than light without breaking any laws at all. So what if, just what if, there is a way to step sideways through the rules, not by smashing the speed limit, but by quietly folding the road beneath our feet? And that thought, well, it changes everything, because suddenly the universe no longer feels locked. It feels as though it might be listening. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. When we talk about distance in everyday life, we do it casually, almost carelessly. A few kilometers to work, a few hours to visit family, a flight across an ocean that fits neatly into a single day, and our brains are rather good at that scale. They evolved for it after all. But then we lift our eyes to the night sky and the language itself breaks down. Because out there, distance is no longer measured in meters or miles. It is measured in time, in years of light traveling through the dark. And that's the thing. The universe quietly insists that space and time are inseparable companions. One cannot be spoken of without the other. Well, the stars are not just far away. They are far back in time. And every point of light is a message sent long before any of us were here to receive it. You see, the gap between stars is so vast that astronomers long ago gave up trying to express it in familiar units. Instead, they turned to the light year, a measure that tells us not how far something is in space, but how long it takes light itself to cross that distance. And light is astonishingly fast. It can circle the Earth more than 7 times in a single second. Yet even at that extraordinary speed, the nearest star beyond our sun is more than 4 years away. And, pause on that for a moment. 4 years. That is a child growing into a different version of themselves, entire chapters of a human life passing by, just for a single beam of light to make the journey. And once you accept that, once it truly settles in, the Milky Way becomes something else entirely, no longer a gentle band of stars, but a structure of almost unimaginable scale, stretching across roughly 100,000 light years, which means that a signal leaving one edge of our galaxy when early humans first painted on cave walls would not yet have reached the other side, and perhaps never will in our lifetime, or in the lifetime of our species. And I suppose that realization carries a quiet weight, because it tells us that the universe is not merely big. It is structured in a way that resists urgency. It does not hurry. It does not care how curious we are. Our spacecraft, brave and brilliant as they are, only deepen this sense of scale. We celebrate their launches with countdowns and fire and thunder, and rightly so. They represent the best of human ingenuity. But once they leave Earth, They are swallowed by a cosmic stillness that makes their speed feel almost irrelevant. Voyager 1, for example, has been traveling for nearly half a century, racing away from the sun faster than any human-made object before it, and yet it has only just begun to leave the sun's gravitational neighborhood. Not even the galaxy, just the faint outer influence of our own star. And that's rather humbling, because it means that even our fastest messengers are barely crawling across the first tile of a vast cosmic floor. Even if we imagine a spacecraft that could travel at a staggering fraction of the speed of light, say 99% of it, which already lies far beyond our current capabilities, the journey to nearby stars would still stretch across years from our perspective. And for longer journeys, across generations, a trip across the Milky Way would take longer than recorded human history, and the people who launched the mission would never meet those who arrived, and perhaps not even those who arrived would meet the end of it. And, that's not just an engineering problem, that's a cultural and philosophical one. It forces us to ask what exploration really means when the explorer and the destination can never coexist in time. So the universe becomes, in a sense, a prison built not of bars but of patience. Its walls are made of distance, and its locks are forged from the speed of light. And there is no malice in it, no intention, just the quiet consequence of how space-time is shaped. And that's the unsettling part, because it tells us that ambition alone is not enough. Courage is not enough. Even intelligence may not be enough. The universe is structured in a way that does not easily yield to desire. And yet, perhaps, this is where curiosity does its finest work. Because when faced with a wall that cannot be climbed, the human mind does something rather remarkable. It steps back and asks whether the wall is real in the way we think it is, or whether there might be a door hidden in its geometry, and that's exactly what physicists began to do when confronted with these cosmic distances. Instead of asking how to build faster ships, they began to question the nature of motion itself. Because all of our traditional ideas about travel rely on the same basic assumption that you move an object through space, pushing against something, throwing mass behind you to go forward. And well, when space is this vast, that assumption begins to feel fragile. You see, every journey we have ever taken, from walking across a room to launching a rocket, is a negotiation with inertia and energy. And the faster we want to go, the more energy we must spend. But in the cosmic arena, the price rises dramatically, and distance compounds the cost. And I suppose that is why interstellar travel feels so unattainable. Not because we lack imagination, but because the rules themselves seem stacked against us. And there is another subtle cruelty hidden in these distances. Communication. Even if we could send people to the stars, talking to them would be painfully slow, a conversation stretched across decades, questions arriving long after the context that gave birth to them has faded, and answers returning to a world that has already changed. So the universe not only separates us physically, it isolates us temporally. It turns dialogue into archaeology and presence into memory. But perhaps that is not the end of the story. Perhaps this sense of confinement is an invitation rather than a verdict, because the same physics that imposes these limits also hints at something deeper, something more flexible beneath the surface. Einstein showed us that space is not a static backdrop. It can stretch and curve and respond to energy and mass. And in the early moments after the universe began, space itself expanded faster than light, carrying galaxies apart without violating any laws at all. And that fact sits quietly in the background, waiting to be noticed. So when we feel trapped by distance, when the stars seem locked away behind an unbreakable speed limit, it may be that we are still thinking too traditionally, still imagining engines straining against an unyielding void. And maybe the next step is not about pushing harder, but about understanding the medium we are moving through, because if space itself can stretch, if it can flow, then perhaps motion does not have to look the way it always has. And perhaps the prison is not as solid as it first appears. It may simply be that we have been rattling the wrong bars, and the real question now becomes not how fast we can go, but how we choose to move at all. And so, if the prison is not only distance, but the way we attempt to cross it, then the next thing we must look at, quietly and honestly, is the machinery we trust to carry us forward, because all of our hopes of movement are bound up in engines, you see, in the idea that if we push hard enough, long enough, we will eventually arrive somewhere new, and that idea feels intuitive, almost comforting, because it mirrors how we move through our everyday lives. We walk by pushing against the ground. Cars move by pushing air and asphalt aside. Airplanes carve their way through the sky by throwing air backward, and rockets, well, they are simply the most extreme version of this ancient bargain, motion in exchange for sacrifice. Every rocket engine humanity has ever built follows the same basic logic. You take mass, you accelerate it violently in one direction, and by the grace of conservation of momentum, you move in the opposite direction. And, it is an elegant principle, one that works astonishingly well on Earth and even within our solar system. It lifted us off our planet. It carried us to the moon. It sent probes past the outer planets. And for a while, it made us believe that the universe was simply an extension of the road we had already started walking. But the deeper we look into space, the more this logic begins to betray us, because the universe is not a road. It is an ocean without shores, and rockets are ships that must carry not only their destination, but the fuel for every single moment of the journey. And that's the thing. Every kilogram of fuel you add must itself be accelerated, which means it demands even more fuel to push it, and that extra fuel must also be accelerated, and suddenly you are caught in a loop, a spiral of increasing mass and diminishing returns. And this is not a flaw in engineering. It is not something that better materials or smarter computers can simply fix. It is written into the physics itself. The rocket equation, as cold and mathematical as it sounds, tells a deeply human story. It says that to gain a little more speed, you must pay a little more mass. And as you chase higher speeds, the cost rises not gently, but brutally, exponentially. And that word exponential is important here, because it means that progress does not scale kindly. It accelerates away from you. The closer you get to your goal, the more unreachable it becomes. Imagine designing a ship meant to travel between the stars using conventional propulsion. At first it seems manageable. You sketch out engines, tanks, habitats, and then you begin adding fuel. Lots of fuel, because the distances are immense, and as the fuel tanks grow, so does the mass of the ship, which means the engines must grow stronger, which means they require even more fuel. And before long, the ship is no longer a vessel. It is a flying fuel depot, dragging itself forward with monumental effort just to gain a tiny increase in speed. And even if you indulge in the most optimistic assumptions, perfect efficiency, materials that never fail, engines that operate flawlessly for centuries, you still cannot escape the arithmetic, because the faster you want to go, the more your ship becomes fuel, until there is almost nothing left that resembles a place for humans at all. And I suppose that is a rather sobering realization, because it tells us that interstellar travel is not being held back by a lack of ambition or imagination, but by a fundamental mismatch between our methods and the scale of the universe. There is also the matter of energy, because fuel is simply stored energy waiting to be released, and the amounts required for relativistic speeds are staggering. To push a modestly sized spacecraft to a significant fraction of the speed of light would require energy comparable to the total output of entire civilizations, sustained over long periods of time. And that is not a question of better engines. It is a question of where such energy could possibly come from, and how it could be stored, controlled, and directed without destroying the very ship it is meant to propel. Nuclear fusion, often invoked as a kind of cosmic miracle, does improve matters. It offers far more energy per unit mass than chemical fuels, but even fusion only softens the curve. It does not flatten it. Antimatter, the most energy-dense fuel we know of, brings its own nightmares. Production is vanishingly inefficient, storage is precarious beyond imagination, and the slightest containment failure would be catastrophic. And yet even with antimatter, the dream of routine interstellar travel remains stubbornly out of reach. So we find ourselves in a trap, a beautifully constructed one. Every solution that follows the traditional path leads us deeper into the same maze. Bigger engines demand more fuel demands bigger engines, and the universe watches patiently as we run in circles. And that's the quiet cruelty of it, because nothing appears broken. Everything works exactly as it should, just not in our favor. And perhaps this is why the history of spaceflight, for all its triumphs, also carries an undertone of melancholy. Each probe that leaves the solar system does so alone, uncrewed, silent, carrying golden records and faint whispers of who we were. Because sending people, with all their fragility and needs, multiplies every challenge beyond reason. Life support, shielding, psychology. Time itself becomes an adversary, stretching journeys into spans longer than any individual life. When we talk about generation ships, vast arcs, drifting between the stars for centuries, we are not really talking about engineering, we are talking about surrender. Surrender to the idea that travel means never arriving. That exploration means becoming a story told by descendants who were never meant to see Earth at all. And while that vision is poetic, it is also an admission that our engines have failed us at the scale we truly wish to explore. And so the uncomfortable truth begins to emerge. The universe is not denying us travel because we lack technology. It is denying us because we are asking the wrong question. We keep asking how to push harder, how to throw more mass behind us, how to squeeze a little more efficiency from the same old bargain. But the bargain itself is the problem. Motion through space by reaction. Mass works wonderfully when space is small, but when space becomes cosmic, it turns against us. This is why engineers, no matter how brilliant, always run into the same wall when they extrapolate rocket designs to interstellar distances. The equations do not care about optimism. They do not bend to vision. They simply state the cost again and again until the numbers become absurd. And at that point, you realize you are no longer designing a ship. You are designing a monument to the limits of propulsion. And that realization, well, it changes the tone of the conversation. Because once you accept that traditional engines cannot take us where we want to go, you are forced into a more radical line of thought, one that feels almost philosophical. You begin to wonder whether motion itself has been misunderstood, whether the act of traveling must always involve crossing space step by step, or whether that is merely an assumption inherited from our experience on a small, slow planet. You see, physics does not actually say that space is immutable. It does not insist that distances are fixed and absolute. That assumption comes from our intuition, not from the equations. And buried within the very theories that limit our engines are hints that space can behave in ways that defy everyday logic. It can stretch, it can compress, it can curve in response to energy and mass. So perhaps the failure of traditional propulsion is not a dead end, but a signpost, pointing us away from engines and towards something more subtle, more profound. Because if pushing against space is futile, then the only option left is to understand space itself, to ask whether it can be shaped, persuaded, or guided in ways that render engines almost irrelevant. And that question, once asked, leads us inevitably toward Einstein, toward the strange and beautiful idea that the universe has a speed limit not because it wants to imprison us, but because it is inviting us to think differently about what it means to move at all. And so the trail of thought carries us naturally to the heart of the matter, because once we abandon the hope that engines alone can save us, we are forced to confront the rule that stands quietly behind every failure, the rule that seems almost personal in its stubbornness. The speed of light, you see. It is often spoken of as if it were merely a technical detail, a number written in textbooks. But in truth, it is something far deeper. It is woven into the structure of reality itself, and it was Einstein who showed us just how profound that weaving truly is. Before Einstein, space and time were thought of as separate things, a kind of stage on which the universe performed its grand play. Objects moved through space, clocks ticked through time, and speed was simply distance divided by duration. A rather innocent idea, and it served us well at human scales. But when Einstein looked closely, when he asked what would happen if you chased a beam of light, the old picture quietly fell apart, because light refused to behave like anything else. It did not slow down when observed. It did not add or subtract its speed depending on who was watching. It simply was, constant, unwavering, the same for all observers, no matter how fast they moved. And that simple, unsettling fact forced a radical conclusion. Space and time could not be separate after all. They had to adjust themselves to preserve the constancy of light, and so they fused into space-time, a single fabric where distances and durations bend and stretch depending on motion. And that's the thing. Once space-time enters the story, speed stops being just a number. It becomes a boundary between what is possible and what is forbidden. Special relativity tells us that as an object accelerates, something curious happens. Its energy increases, of course. That part feels intuitive, but its resistance to further acceleration also increases, not because of friction or mechanical strain, but because motion itself is altering the geometry of space-time around it. And, from the perspective of an external observer, the object's effective mass increases, not in a literal sense of adding matter, but in the sense that it becomes harder and harder to push, demanding more energy for smaller and smaller gains in speed. As you approach the speed of light, this effect becomes extreme. The energy required to accelerate further does not merely rise, it skyrockets, racing toward infinity. And that word infinity is not poetic here. It is mathematical. It means there is no finite amount of energy that can push a massive object all the way to the speed of light, let alone beyond it. And I suppose that is one of the most humbling conclusions in all of physics, because it tells us that no matter how advanced a civilization becomes, no matter how clever or determined, there are doors that cannot be opened by force alone. Particle accelerators offer us a glimpse of this limit in action, deep underground. Physicists hurl subatomic particles around vast rings, feeding them energy again and again, and each time the particles respond with diminishing enthusiasm, their speeds inch closer to light, but never quite reach it, and the energy invested grows colossal, entire power stations devoted to shaving the tiniest fraction off the remaining gap. And even at this microscopic scale, the universe holds firm. The speed limit is enforced not by decree, but by geometry. And this is why the dream of outrunning light feels so tantalizing and so cruel. Because light itself is massless, it does not experience time the way we do. From its perspective, if such a perspective can be meaningfully imagined, emission and arrival are the same event. But the moment you add mass, the moment you try to carry information, matter, or people, you are bound to the slower rhythm of space-time, and the faster you try to go, the more space-time resists. So the wall we face is not technological. It is not about engines or fuel or materials. It is a wall built from the equations themselves, tested and retested, not just in thought experiments, but in laboratories, in satellites, in the very GPS signals that guide our phones and planes. Relativity is not an abstract theory. It is quietly at work every day, correcting clocks in orbit, bending time just enough to matter, and that everyday reliability makes its cosmic implications all the more unavoidable. Near the speed of light, time itself begins to behave strangely. Clocks on a fast-moving ship would tick more slowly compared to those left behind. Lengths along the direction of motion would contract, the universe rearranging itself to preserve the cosmic speed limit. And while this might sound like a loophole, a way to cheat distance by experiencing less time, it does not help from the outside perspective. The journey still takes years or centuries for the universe at large, and the energy cost remains crushing. And so relativity offers no escape through clever bookkeeping. And perhaps the most decisive blow comes when we consider what happens exactly at the speed of light. The equations break. Mass would require infinite energy. Time dilation would become absolute. Lengths would collapse. The mathematics simply refuses to go there. And that refusal is not a gap in our knowledge. It is a statement, a declaration that space-time itself draws a line and says, no further. It is tempting, of course, to imagine future discoveries overturning this limit, to hope that some deeper theory will come along and grant us permission to break free. But every attempt so far to unify physics, to reconcile relativity with quantum mechanics, has preserved this boundary, not weakened it. If anything, It has reinforced the idea that the speed of light is not just a feature of our universe, but a structural necessity, a cornerstone of causality itself. Because once you imagine exceeding the speed of light, another problem emerges, one that is even more unsettling. Cause and effect begin to unravel. Events can appear to happen before their causes. Signals can arrive before they are sent. Time loops back on itself, and the orderly narrative of the universe dissolves into paradox. And that is not just philosophically troubling. It is physically catastrophic, because the universe we observe, the one that forms stars and planets and people, relies on causality to function at all. So relativity does not merely tell us that faster-than-light travel is difficult. It tells us that it is incompatible with the very idea of a consistent universe, and that is why this barrier has held firm despite decades of speculation, because it is supported not by a single equation, but by an entire framework of understanding that has proven astonishingly resilient. And yet, and this is where the story takes a subtle turn, relativity also contains a quiet hint of something else, something that feels almost like a whisper behind the wall, because while it forbids objects from moving through space faster than light, it does not forbid space itself from changing, from stretching or contracting. And this distinction is crucial. It is the thin seam where possibility begins to glimmer. Einstein's own work on general relativity showed us that space-time is dynamic, that it responds to mass and energy, that gravity itself is not a force in the traditional sense, but the curvature of space-time. And once you accept that, you begin to see that motion might not require outrunning light. It might require reshaping the stage on which motion occurs. The early universe offers a striking example. During its infancy, space expanded at a rate that effectively separated regions faster than light could travel between them. And yet no laws were broken, no causality violated, because nothing was locally moving faster than light. Space was simply growing, carrying everything with it. And I suppose that realization sits there, quietly provocative, because it tells us that the speed limit applies to motion through space, not to space itself. So we arrive at a strange and beautiful tension. On one hand, special relativity erects an unbreakable wall against faster-than-light travel by any object with mass. On the other hand, general relativity reveals that space is malleable, capable of expansion and contraction, capable of doing the very thing we are forbidden to do ourselves. And that tension is not a contradiction. It is an invitation. If engines fail because pushing against space is futile, and if light speed is an absolute boundary for objects, then perhaps the only remaining path forward is not to fight these truths, but to work with them, to ask whether the universe itself can be persuaded to carry us, rather than resist us. And that question, once it takes root, leads naturally to the next uncomfortable inquiry. Not just can we move faster than light, but why doing so might be dangerous at all, and what the universe is protecting when it draws such a firm line in the fabric of space-time. And so, standing at that boundary where relativity draws its uncompromising line, we begin to sense that the speed of light is not merely a technical inconvenience, but a guardian of something far more fragile, because the moment we imagine crossing it, really crossing it, not bending space or finding loopholes, but simply pushing an object faster than light, the universe responds not with resistance, but with contradiction. And, that is where the danger truly lies. You see, at the heart of physics, there is an assumption so basic we rarely notice it, the assumption that causes come before effects, that a spark ignites a flame, that a message is sent before it is received, that time flows in one direction, quietly, reliably, like a river that never turns back on itself. And this assumption is not philosophical decoration, it is structural. It is what allows the universe to be intelligible at all, and the speed of light is woven directly into that structure. In Einstein's space-time, the speed of light acts as a kind of cosmic referee. It defines which events can influence one another, drawing invisible cones of possibility around every moment. Inside these cones, causes can lead to effects. Outside them, events are forever disconnected. And that's the thing. Faster than light travel does not merely bend these cones, it shatters them. It allows signals to leap outside their causal boundaries, and once that happens, time itself begins to lose its footing. Imagine sending a message faster than light, from one place to another. And now imagine another observer moving relative to you because relativity insists that motion is always relative. And for that observer, the order of events can change. The message may appear to arrive before it was sent, not metaphorically, but mathematically. And suddenly you are faced with a universe where effects precede causes, where information arrives from the future, where decisions can be undone by messages that have not yet been written. This is not science fiction exaggeration. It is a direct consequence of the equations, and physicists have traced these paradoxes again and again, finding that faster-than-light signals inevitably open the door to closed loops in time, scenarios where an event is both the cause and the result of itself. Logical knots with no consistent solution, and when logic collapses, physics follows. The universe we observe is astonishingly stable. Stars burn predictably. Atoms behave consistently. Histories unfold without contradiction. And this stability rests on causality. Break it, and the entire edifice trembles, because without a clear order of events, there is no way to define what happens and what does not. Reality becomes ambiguous, undecidable, and that is not a universe that can support complexity, let alone life. So when physics forbids faster-than-light travel, it is not being conservative, it is being protective. It is safeguarding the arrow of time itself, ensuring that the universe does not descend into a haze of paradox. And I suppose that reframes the speed limit entirely. It is not a punishment. It is a stabilizer, a necessary constraint that allows anything at all to exist in a coherent way. And this is why attempts to casually dismiss the light barrier often falter, because they underestimate the depth of what is at stake. It is tempting to say that future theories will simply wave away these concerns, that paradoxes will be resolved somehow, but every consistent framework we have built so far reinforces the same conclusion. Causality and the speed of light are inseparable. Tamper with one, and the other unravels. Time travel, for instance, often appears as a playful idea in stories, but in physics it is a warning sign. Closed time-like curves, paths through space-time that loop back on themselves, arise naturally when faster-than-light motion is allowed. And while mathematics can describe such curves, their physical interpretation is deeply troubling, because they allow information to exist without origin, events without cause. And that kind of universe is not just strange, it is fundamentally broken. So the danger of exceeding the speed of light is not that we would crash into something or tear ourselves apart. It is that we would undermine the logical order that makes crash and safety meaningful concepts in the first place. And that is perhaps the most unsettling realization of all, because it suggests that some limits are not negotiable, not because we lack power, but because exceeding them dissolves the very framework in which power makes sense. And yet, and this is where the story remains delicately balanced, these dire consequences apply specifically to motion through space-time, to objects and signals outrunning light within the fabric of the universe. They do not apply to space-time itself changing shape, and that distinction is subtle but crucial, because while faster-than-light motion leads to paradox, faster-than-light expansion does not. The universe itself demonstrates this beautifully. In its earliest moments, space expanded so rapidly that regions were carried apart faster than light could travel between them, and yet causality remained intact locally. No object outran a light beam in its immediate neighborhood. Space simply grew between them, stretching the distance without violating the cosmic speed limit, and I suppose that example sits there like a quiet hint, a reminder that the universe already knows how to separate faster than light without tearing itself apart. This tells us something profound. The danger is not speed alone. It is the way speed is achieved. Push an object through space too fast, and causality collapses. Reshape space itself, and the rules remain unbroken. And that difference is everything. So physics does not merely say no to faster than light travel. It says no to a specific method, to brute force defiance of space-time's structure. And by doing so, it nudges us toward a more nuanced approach, one that respects causality while exploring the flexibility of space itself. But even if we accept this, even if we promise never to violate causality, another problem looms, one that feels more practical, more immediate: energy. Because whether we push through space or attempt to shape it, the universe demands payment, and that payment is measured in staggering amounts of energy, far beyond anything we have ever controlled. And so, having learned why the light barrier exists and why smashing through it would unravel the universe, we are led almost reluctantly to the next sobering question. Even if we find a lawful path around this limit, even if causality remains intact, do we have the means to pay the cosmic price? Or is energy itself the final gatekeeper, quietly waiting to remind us that understanding the rules is only the beginning of the journey? And so, having accepted that causality must be protected, and that brute force speed is forbidden, we arrive at what may be the most unforgiving barrier of all: energy. Because even the most elegant ideas in physics are ultimately grounded in a simple demand. Nothing happens without payment, and the universe is meticulous in its accounting. You see, it does not accept promises or optimism. It asks only how much energy you have, and whether it is enough. When we talk about accelerating an object, any object, what we are really talking about is changing its energy state, lifting it to a higher rung on the ladder of motion. And for small speeds, the cost feels manageable, familiar even. But as speed increases, the price does not rise gently. It surges. And by the time you are thinking about relativistic velocities, the numbers stop feeling like engineering problems and start feeling like geological or stellar ones. Consider something deceptively simple: a spacecraft with a mass of 1 ton, not a city in space, not a generation ship, just a modest vehicle. To accelerate that mass anywhere near the speed of light would require an amount of energy comparable to the total energy produced by all of humanity over extended periods of time. And that's the thing. This is not an exaggeration or a rhetorical flourish. It falls straight out of the equations, and once you see it written down, it is almost shocking how quickly the figures escape the realm of the possible. Energy, unlike distance, is not something you can negotiate with. You cannot stretch it with clever geometry or reinterpret it with perspective. It must be generated, stored, and released, and each of those steps carries its own limits. Chemical energy, the kind that powers rockets today, is woefully inadequate. It served us well to leave Earth, but it barely scratches the surface of what interstellar travel demands. Nuclear fusion, often hailed as the fire of the stars brought down to Earth, does offer a dramatic improvement. It unlocks millions of times more energy per unit mass than chemical reactions. And it is genuinely transformative for many applications, but even fusion begins to look small when set against the energy required to push large objects to relativistic speeds. It moves the needle, but not nearly far enough. Antimatter, the most concentrated form of energy we know, is often invoked as the ultimate solution, because when matter and antimatter meet, nearly all their mass is converted directly into energy, a perfect exchange. And yet this perfection is precisely what makes antimatter so treacherous. Producing it requires enormous amounts of energy in the first place, far more than we ever get back. Storing it demands containment systems of almost unimaginable precision, and a single failure would release energy with devastating consequences. And, even if we solved all of that, even if antimatter were cheap and safe, the total energy budget still strains credulity. There have been serious studies, earnest and detailed, that attempt to chart a path forward. Concepts like interstellar probes powered by fusion or antimatter, and one of the most famous, the Daedalus Project, imagined a fusion-powered spacecraft capable of reaching a significant fraction of the speed of light. But when the numbers were tallied, the result was sobering. Vast amounts of fuel, monumental costs, and a final speed that, while impressive, still left the stars frustratingly far away in human terms. And that is the recurring pattern. Every time we push the calculations forward, every time we assume better technology, higher efficiency, bolder designs, the same wall emerges: energy requirements that scale beyond practicality, beyond sustainability, beyond anything that could reasonably be devoted to a single journey, And I suppose that is when it becomes clear that the problem is not courage or intelligence, it is scale. Energy at these levels is not something you casually divert, it reshapes civilizations. To harness it would require infrastructure on a planetary or even stellar scale, entire economies devoted to feeding a single mission, and the question then becomes not, can we do it, but should we, and for whom? Because the opportunity cost is immense. Every joule spent on pushing a ship closer to light speed is a joule not spent sustaining life, healing ecosystems, or preserving the fragile balance of our own world. And there is another layer to this problem, one that is often overlooked. Energy does not just need to be produced. It needs to be managed, directed, controlled. Releasing enormous amounts of energy in a confined space risks tearing the ship apart, bathing it in radiation, or destabilizing the very space-time it is meant to traverse. And, these are not minor engineering challenges. They are fundamental constraints imposed by physics itself. Heat dissipation alone becomes a nightmare, because every inefficiency, every lost fraction of energy must go somewhere. And in the vacuum of space, shedding heat is remarkably difficult. A ship capable of handling relativistic energies would glow fiercely in infrared, radiating away waste heat like a miniature star. And that glow is not just an inconvenience. It is a structural stress, a continuous assault on materials pushed to their limits. So energy emerges as the final gatekeeper, standing calmly where engines, relativity, and causality have already turned us away. And it does so without drama, without hostility, simply by insisting on payment that is far beyond our means. And perhaps that is the most humbling aspect of all, because it tells us that the universe is not impressed by ambition. It responds only to balance sheets written in the currency of energy. Yet even here, even at this seemingly insurmountable barrier, there is a quiet twist, because energy, like space, is not always where we expect it to be. The universe is not empty. It is filled with fields, fluctuations, and structures that store vast amounts of energy in subtle ways. And, once again, the failure of our conventional thinking becomes apparent. We have been imagining energy as something to be carried, like fuel in a tank, something that must be hauled across the cosmos along with the ship. But that assumption may be just as limiting as the idea that engines must push against space, because the universe itself is rich with energy, locked into the fabric of space-time, waiting not to be consumed, but to be shaped. This is where the conversation begins to shift, almost imperceptibly, away from the language of propulsion and toward the language of geometry, because if moving through space is too expensive, perhaps the alternative is to change the space you are moving through, to exploit the fact that space-time itself contains energy and responds to it, and that response can, under the right conditions, do work on your behalf. In general relativity, energy and space-time are inseparable. Energy tells space-time how to curve, and curved space-time tells matter how to move. And that circular relationship is not just a poetic description. It is the core of gravity itself. Planets orbit not because they are pulled, but because they follow the contours of curved space-time, falling endlessly without ever reaching the ground. So perhaps the lesson of this energy crisis is not that travel is impossible, but that we have been budgeting incorrectly, focusing on brute force expenditure rather than structural manipulation. And that realization leads naturally to a more radical question, one that feels almost upside down. Instead of asking how much energy we need to move a ship, what if we ask how to make space do the moving for us, using its own dynamics, its own stored energy, its own flexibility? Because if energy carried is never enough, then the only remaining hope is energy arranged, and that thought, once entertained, opens the door to a different way of thinking entirely, a reversal of perspective that shifts our attention away from engines and fuel and toward the deeper behavior of space-time itself. And it is there, in that reversal, that the next chapter of this story quietly begins. And so, with every conventional path exhausted, with engines defeated by mass, light speed defended by causality, and energy standing like an uncompromising accountant at the edge of imagination, physics does something rather beautiful. It turns the question inside out. because when a problem refuses to yield to force, the only remaining option is to change perspective. And that is exactly what happens here. You see, instead of asking how a ship might move faster through space, physicists begin to ask a question that at first sounds almost absurd. What if the ship does not move at all? This is not a retreat from ambition. It is a deeper kind of boldness because it requires letting go of our most ancient intuition, the idea that travel means motion, that to go somewhere you must cross the space in between, step by step, moment by moment. And that intuition is deeply rooted in our bodies, in the way our muscles work, in the way we experience effort. But the universe, it turns out, does not share our intuitions. In Einstein's general relativity, space is not a passive stage. It is an active participant. It stretches, it compresses, it curves, and it responds dynamically to energy and mass. Gravity itself is not a pull, but a geometry. Objects simply follow the contours of space-time, like marbles rolling along a warped surface. And that's the thing. If space can curve enough to trap light around a black hole, then perhaps it can also curve in ways that change how distance itself behaves. You see, distance is not as absolute as it feels. It is not a rigid ruler laid across the cosmos. It is a measure that depends on the shape of space-time between 2 points. Stretch that space, and distance grows. Compress it, and distance shrinks. And this is not speculation. It is observed every day on the largest scales. The universe is expanding. Galaxies are carried apart, not because they are moving through space, but because space itself is growing between them. In the early universe, this expansion was extreme. Space inflated so rapidly that regions were separated faster than light could travel between them, and yet nothing locally broke the speed limit. No particle outran a photon in its own neighborhood. Space-time itself did the moving, and causality remained intact. And I suppose that moment in cosmic history is one of the most important clues we have, because it demonstrates, unequivocally, that faster than light separation is not forbidden, only faster than light motion through space is. So the question quietly transforms. Instead of how do we push a ship faster, it becomes how do we arrange space-time so that the destination comes to the ship, or the ship arrives at the destination without ever locally exceeding the speed of light. And once framed this way, what once seemed impossible begins to look merely improbable. This reversal of thinking is subtle but profound. It requires us to stop imagining spacecraft as projectiles and start imagining them as passengers. Not passengers in the usual sense, but passengers carried by space-time itself, embedded in a region of geometry that moves not by velocity, but by distortion, and that is a very different kind of travel. Consider a simple analogy. Walking on a moving walkway at an airport, you are not walking faster relative to the floor beneath your feet, but you arrive at your gate sooner because the floor itself is moving, your local speed is unchanged, yet your effective progress through the terminal is greater. And while this analogy is imperfect, it captures the essence of the idea: motion without effort, speed without acceleration. In general relativity, there is nothing that forbids space-time from being arranged this way. The equations allow for regions where space ahead contracts, while space behind expands. And within such a region, an object could remain at rest relative to its local surroundings while still being carried across vast distances. And the speed of light would never be violated locally. Causality would remain unbroken, and the universe would remain logically consistent. This is the loophole, the legal one, the one that physics itself quietly permits. And it is not hidden or obscure. It has been there since Einstein wrote down the field equations, waiting for someone to ask the right question. And I suppose that is often how progress happens, not by discovering new laws, but by learning to listen more carefully to the ones we already have. But of course, possibility on paper is not the same as feasibility in reality, and the moment this idea is taken seriously, a cascade of further questions follows. What kind of energy distribution would be required to shape space-time in this way? How stable could such a configuration be? What would it mean for the occupants inside? And perhaps most importantly, is there any precedent, any hint that space-time can be manipulated deliberately rather than merely endured. Here again, gravity provides a clue. Massive objects already shape space-time. Stars curve it gently, planets more subtly, black holes dramatically. And these curvatures have real, measurable effects. Time slows, paths bend, horizons form. And that tells us that space-time is responsive. It is not rigid, and responsiveness implies, at least in principle, controllability. The challenge, then, is not whether space-time can move. It demonstrably can. The challenge is whether we can learn to guide that movement, to engineer curvature rather than merely observe it. And, that is where the conversation shifts from despair to cautious curiosity, because engineering space-time is a daunting prospect, but it is not obviously forbidden. The key insight here is that space-time responds to energy density, not just mass in the traditional sense. Pressure, tension, and even exotic forms of energy all contribute to curvature, and this broad definition opens a wider design space than one might initially expect. It suggests that the universe is sensitive not just to how much energy exists, but to how it is arranged. This arrangement matters immensely. A uniform distribution of energy produces a very different space-time geometry than a sharply concentrated one, and clever configurations can, at least mathematically, produce highly non-intuitive effects, including regions of expansion and contraction that move relative to one another. And, this is where the dream of effective, faster-than-light travel quietly re-enters the conversation, not as rebellion against physics, but as compliance with its deeper rules. What makes this idea especially compelling is that it reframes the energy problem as well. Instead of needing to supply energy continuously to accelerate a ship, the energy is invested in shaping space-time itself, creating a persistent geometry that does the work, like building a canal rather than rowing endlessly against a river. And while the initial cost may still be enormous, the efficiency gains could be transformative. This does not mean the problem is solved, far from it. Shaping space-time on demand is an engineering challenge unlike anything humanity has ever faced, and, it may require forms of energy or matter that we barely understand. But the important shift is conceptual. The wall that once seemed absolute now reveals a doorway, narrow and difficult to pass through, but undeniably present. And there is a deeper philosophical resonance here as well, because this reversal of thinking mirrors something fundamental about our relationship with the universe. We have long assumed that progress means domination, pushing harder, extracting more, forcing our will onto nature. But again and again, physics teaches us a gentler lesson, that true power lies in alignment, in understanding the grain of reality and moving with it, rather than against it. So when physicists ask how space might move instead of how a ship might move faster, they are not abandoning ambition. They are refining it, tuning it to the structure of the cosmos itself. And I suppose that is why this idea feels so elegant. It respects the speed of light. It preserves causality. It acknowledges the energy constraints, and yet it still offers a path forward. But of course, an idea is only as strong as its details, and once this question is taken seriously, once it is allowed to sit at the center of the conversation, the next step becomes unavoidable. Someone must ask not just whether space-time can be shaped, but what such a shape would actually look like. What geometry would allow a region of space to move relative to the rest of the universe in this peculiar way? And it is here, at this precise moment, that a specific concept begins to emerge from the mathematics, something once relegated to fiction, now appearing, unexpectedly, in the equations themselves, the idea of a bubble of space-time, carrying its contents along, not by speed, but by curvature. And it is here, at this quiet crossroads between mathematics and imagination, that the idea finally takes a recognizable shape. Because once you ask how space-time itself might move, the equations of general relativity answer not with poetry, but with geometry. And sometimes geometry can be more astonishing than any story we invent. You see, in the mid-1990s, a physicist named Miguel Alcubierre asked a deceptively simple question: if space-time can expand and contract, what would happen if it did so in a very particular way? He was not trying to build a spaceship, not really. He was exploring the freedom allowed by Einstein's equations, and what he found was something extraordinary, a solution in which a region of space-time could be shaped into a kind of bubble, flat and calm on the inside, while the space around it behaved very differently. Space in front of the bubble would contract, shrinking the distance to whatever lay ahead, while space behind it would expand, stretching the distance left behind. And, taken together, these two effects would cause the bubble to move. The remarkable part is that nothing inside the bubble would be moving through space at all. From the perspective of the occupants, they would be at rest, floating peacefully in a pocket of normal space-time, no crushing acceleration, no relativistic distortions, no violation of local physics. And yet, relative to the outside universe, the bubble itself could move arbitrarily fast, even faster than light, because it is not the contents that are moving. It is the space-time geometry carrying them along. This is the essence of what has come to be called a warp bubble, and that phrase, so often associated with fiction, suddenly found itself grounded in real mathematics, not as an engineering proposal, but as a proof of principle, a demonstration that the laws of physics do not explicitly forbid this kind of motion. And I suppose that moment marked a subtle shift, because it showed that faster-than-light effective travel is not automatically synonymous with broken physics. In this picture, the ship does not outrun a beam of light in its local frame. Light behaves normally inside the bubble. Clocks tick at ordinary rates. Rulers measure ordinary distances. And causality remains intact because locally, nothing ever exceeds the speed of light. The bubble simply rearranges the space-time outside, shortening the path ahead and lengthening the path behind. And from the outside, it looks as though the ship has leapt across space faster than light. But from the inside, nothing extraordinary has happened at all. This duality is deeply characteristic of relativity. What looks impossible from one frame becomes trivial from another, and the warp bubble is perhaps the most dramatic example of this principle applied to motion itself. It is not cheating the rules. It is exploiting their flexibility, and that distinction matters immensely. Now, it is important to pause here because the word bubble can mislead. This is not a physical shell or a force field in the familiar sense. It is a region defined entirely by geometry, by how distances are measured, by how space-time is curved, and that makes it both elegant and unsettling, because geometry is not something we are accustomed to engineering directly. In Alcubierre's solution, the space-time inside the bubble is flat, meaning that occupants would not feel gravity or acceleration, while the distortion is confined to a ring or shell around the bubble, where space-time is being aggressively reshaped, and this shell is where all the exotic behavior lives, the expansion behind, the contraction ahead, and the stresses required to maintain that configuration. And here, inevitably, we encounter the first major complication, energy. Because space-time curvature does not come for free, it requires energy and momentum arranged in very specific ways, and in the case of the warp bubble, the equations demand something unusual, regions of negative energy density, energy that is less than the vacuum itself. And that phrase alone is enough to make any physicist uneasy. Negative energy is not something we encounter in everyday life. It violates our intuitive sense that energy is always positive, always additive. But in quantum field theory, the vacuum is not empty. It seethes with fluctuations, and under certain conditions, those fluctuations can produce regions where the energy density dips below the average vacuum level. And this is not speculation. It has been observed experimentally in phenomena like the Casimir effect. So the warp bubble does not demand something entirely fictional. It demands something rare and extreme, but not fundamentally impossible according to our best theories. And I suppose that nuance is crucial, because it shifts the idea from fantasy to frontier, from impossible to profoundly difficult. The original Alcubierre model, however, was brutally impractical. The amount of negative energy required was enormous, far exceeding anything we could hope to generate or control. Some estimates suggested more energy than contained in the observable universe, which is a rather definitive obstacle. And for a time, this seemed to relegate the warp drive back to the realm of elegant curiosity, mathematically allowed but physically absurd. But physics has a way of refusing to settle so easily, because once a door is opened, even slightly, people begin to ask whether it can be widened. And over the years, other researchers revisited the warp bubble idea, tweaking the geometry, adjusting the shape of the distortion, exploring alternative configurations, and with each iteration, the energy requirements began to come down, sometimes dramatically. What emerged from this work was not a blueprint for a spaceship, but something perhaps more valuable, a demonstration that the initial prohibitive energy estimates were not fundamental, they were artifacts of a particular choice of geometry, and by reshaping the bubble, by making it asymmetric, thicker, smoother, or more localized, the demands could be reduced by many orders of magnitude. This does not mean the problem vanished, far from it. Even the most optimistic models still require energy scales far beyond our current capabilities. But the trend itself was revealing. It suggested that warp bubbles are not a single fragile solution, but a family of possibilities within general relativity, and families can be explored, optimized, and sometimes tamed. Another striking aspect of the warp bubble is that it reframes what speed even means. Because the effective velocity of the bubble is not limited by light speed. It can be set arbitrarily by adjusting the space-time distortion, and this raises a subtle but important point. The bubble does not have a speed in the conventional sense. It is not a particle moving through space. It is a pattern of curvature propagating through space-time. And patterns, as we have already seen in the early universe, are not bound by the same limits as objects. This distinction protects causality, because the bubble cannot be used to send signals backward in time within its own frame. The causal structure inside remains well behaved, and while global questions about causality become more subtle, careful analyses suggest that properly constructed warp bubbles need not produce paradoxes, at least not automatically. And that is an extraordinary statement, because it means the universe may tolerate this kind of motion. From the perspective of a distant observer, the ship appears to cross vast distances in a short time, stars sliding past, light aberrated, horizons shifting. While inside the bubble, the crew experiences something closer to stillness, perhaps even boredom, floating in a quiet pocket of space-time while the universe rearranges itself around them. And I suppose that image is both thrilling and humbling, because it suggests that the most radical journeys might feel deceptively calm. Of course, this calm interior raises further questions. How would one control the bubble? How would it start or stop? How would it steer? Because if the ship itself is not moving, then conventional thrusters are meaningless. Control would have to come from manipulating the space-time distortion itself, and that implies a level of precision and understanding far beyond anything we possess today. There are also questions about interaction with the outside universe. What happens to matter and radiation encountered along the way? How does the bubble interact with interstellar particles, with photons, with gravitational fields? These are not trivial concerns, because the space-time distortion could, in principle, sweep up energy at the front of the bubble, concentrating it dangerously and releasing it upon arrival, and that presents serious challenges for safety and navigation. Yet even these problems, daunting as they are, do not negate the central insight. They refine it. They turn a vague dream into a concrete research program, because for the first time, the idea of faster-than-light effective travel is not merely a story. It is a question with equations, constraints, and testable implications. And perhaps the most profound implication of all is philosophical, because the warp bubble suggests that the universe does not prohibit long journeys. It merely insists that we take them in a way that respects its structure, not by force, but by understanding, not by acceleration, but by arrangement. And I suppose that is a deeply human lesson, echoed across science again and again. So the concept of the warp bubble stands as a bridge, linking the impossibility of brute force travel with the possibility of geometric motion. It does not promise easy answers, but it does promise that the question itself was never foolish, only premature. And yet, as elegant as this idea is, as seductive as its mathematics may be, it immediately confronts us with the hardest problem of all, because shaping space-time on this scale, sustaining a bubble, controlling its dynamics, all of this demands not just energy, but a very particular kind of energy, exotic, negative, precisely distributed, and this brings us face to face with the most stubborn obstacle still standing. Not whether warp bubbles are allowed, but whether the universe provides the ingredients needed to make them real, and whether those ingredients can exist in sufficient quantities outside the chalkboards of theoretical physics. And so, once the geometry is laid bare, and the warp bubble stands revealed as something permitted by the equations, the conversation narrows to a single, stubborn requirement, the kind that physics never lets us ignore for long: energy, but not energy as we usually understand it, not fuel burning in engines or reactions releasing heat, rather a stranger, more unsettling form, because the space-time configuration that gives rise to a warp bubble demands something profoundly unfamiliar: regions where the energy density is negative. Now, that phrase, negative energy, has a way of stopping people in their tracks, because in everyday life, energy is always positive. It is something you add, something you consume, something you run out of. And the idea that energy could be less than nothing feels almost like a violation of common sense. And yet physics, particularly quantum physics, has never promised to respect our intuition. In quantum field theory, the vacuum is not empty. It is alive with fluctuations, fields trembling even in their lowest energy state. And while the average energy of this vacuum is defined as zero, there can be local deviations, fleeting regions where the energy dips below that baseline. And this is not theoretical speculation. It has been measured, most famously in the Casimir effect, where two closely spaced metal plates experience an attractive force because certain vacuum fluctuations are suppressed between them, creating a region of negative energy density. This discovery was quietly revolutionary, because it demonstrated that negative energy is not forbidden by the laws of physics. It exists, albeit in tiny amounts, under very controlled conditions, and I suppose that single fact keeps the warp bubble from being dismissed outright, because the universe itself has shown us that exotic energy states are part of its repertoire. But here is where the scale of the problem asserts itself with brutal clarity. The amounts of negative energy produced in laboratory experiments are minuscule, unimaginably small compared to what would be required to shape space-time on macroscopic scales, let alone around a spacecraft. And the original Alcubierre model demanded negative energy on a cosmic scale, so much that it dwarfed the total mass energy of entire galaxies. At first glance, this seems like the end of the story, a beautiful idea undone by an impossible requirement, but physics rarely ends conversations so cleanly, because the initial estimates were based on a very specific, very idealized geometry, a bubble with sharp boundaries and extreme distortions, and when later researchers revisited the problem, they asked a quieter, more careful question: what if the geometry were gentler? By smoothing out the warp bubble, by spreading the distortion over a larger region, by making it asymmetric rather than perfectly spherical, the energy requirements begin to change, sometimes dramatically, and while they remain enormous, they are no longer absurd in the same absolute sense. They shrink by many orders of magnitude, moving from the impossible toward the merely fantastical. This shift is important because it suggests that the warp bubble is not a single rigid solution, but a design space, a landscape of possibilities within general relativity. And landscapes can be explored, optimized, and sometimes traversed in unexpected ways. And I suppose that is where hope cautiously re-enters the picture. There is also a subtlety here that often gets overlooked. Negative energy does not need to exist everywhere, or permanently. It can be transient, localized, arranged in pulses or shells, and general relativity responds to these distributions dynamically, meaning that clever timing and configuration could reduce the total amount required at any one moment. And this kind of thinking is very familiar to engineers, even if the materials involved are exotic. Another important development is the recognition that not all warp-like geometries require large regions of negative energy. Some alternative metrics allow for effective faster-than-light travel with much smaller negative energy densities, or even with exotic matter distributions that do not strictly violate all classical energy conditions. And while these models are still speculative, they demonstrate that the energy barrier is not a single, immovable wall. At the same time, Quantum inequalities impose strict limits on how negative energy can behave, how much of it can exist, how long it can persist, and over what scales, and these inequalities act like guardrails, preventing runaway violations of causality and stability. They ensure that negative energy cannot be accumulated arbitrarily, and this is where the tension becomes most pronounced, because the requirements of a warp bubble push hard against these quantum limits. So the question becomes not simply whether negative energy exists, but whether it can be organized, sustained, and scaled in a way that satisfies both general relativity and quantum field theory. And that question sits at the frontier of modern physics, right where our understanding begins to fray. And yet, even here, the story refuses to end in despair, because there is a growing sense that our current estimates may still be conservative, shaped by assumptions we do not yet know how to relax, just as early rocket equations once made spaceflight seem absurd before new fuels and techniques emerged. And I suppose that historical parallel is worth holding on to, cautiously, without illusion. There is also the intriguing possibility that the universe itself provides reservoirs of exotic energy on scales we have not yet learned to tap. Dark energy, for instance, permeates all of space, driving its accelerated expansion, and while its nature remains mysterious, it demonstrates that the cosmos is filled with energy forms far stranger than anything we can engineer today, and, it would be premature to assume that all such energies are forever beyond our reach. What makes the energy problem of warp bubbles especially fascinating is that it forces a dialogue between theories that are usually kept separate: general relativity and quantum field theory, the large and the small, geometry and fluctuation, and in trying to reconcile them, we are inevitably drawn toward the deeper question of quantum gravity, the theory that would unify these frameworks and perhaps rewrite the rules entirely. It is entirely possible that in a more complete theory, negative energy behaves differently, or that space-time itself has discrete, quantum properties that make certain geometries easier to realize than our classical calculations suggest, and while this is speculative, it is grounded in the recognition that our current theories are incomplete, powerful, but provisional. So the energy problem, rather than closing the door on warp travel, may instead be pointing us toward new physics, toward insights that would transform not just propulsion, but our understanding of the universe at its most fundamental level. And I suppose that is often how the most stubborn obstacles function in science. They are not barriers, but signposts. There is also a practical shift in tone that accompanies this realization. Researchers are no longer asking when warp drives will be built, but how warp-like effects might be detected, simulated, or approximated in controlled settings, how the principles might be tested without building a starship. And this shift is crucial because it grounds the idea in experiment rather than speculation. By focusing on small-scale analogs, on laboratory systems that mimic certain aspects of space-time curvature using electromagnetic fields, fluids, or plasmas, physicists can begin to explore the behavior of warp-like geometries indirectly, probing their stability, their interactions, their signatures, and, this approach transforms the warp bubble from a distant dream into a research program. And that is where the narrative quietly turns once more. Because if warp geometries can be studied in the lab, if their effects can be simulated and measured, then the question of energy becomes not just theoretical, but empirical. Something that can be constrained, refined, and perhaps gradually tamed, and this marks a profound transition. The warp drive is no longer a single, outrageous proposal demanding impossible resources. It becomes a family of physical effects that can be explored incrementally, and in that incremental exploration, new surprises often emerge. Subtle behaviors, unexpected efficiencies, hints that the universe may be more accommodating than our first calculations suggested. So while the energy requirements of a full-scale warp bubble remain far beyond us, the story does not stall here. Instead, it narrows its focus, shifting from grand journeys to modest experiments, from starships to laboratories, and in doing so, it opens the door to the next chapter, where space-time distortion is no longer just a theoretical construct, but something that leaves traces, signatures, and measurable effects, quietly inviting us to look closer, and listen more carefully to what the universe is already doing. And so the idea quietly steps out of the realm of pure theory and into a very different kind of space, not the vast darkness between stars, but the bright, controlled environments of laboratories here on Earth, because once physicists accept that building a full-scale warp bubble is far beyond us, at least for now, the natural question becomes a gentler one. Can we see even the faintest echo of this idea at small scales? Can space-time be persuaded to whisper rather than shout? This shift in attitude is subtle but profound. It marks the moment when warp physics stops being a thought experiment and becomes an experimental pursuit, not about flying ships, but about probing principles. And this is how science often advances, not by leaping straight to the impossible, but by finding places where reality can be nudged, just enough to reveal its deeper rules. In recent years, researchers have begun to explore analog systems, laboratory setups that do not literally bend space-time, but mimic certain mathematical features of warp geometries using other physical media, light, plasma, electromagnetic fields, fluids, systems where equations that resemble those of curved space-time can be realized and studied, and while these analogs are not space-time itself, they offer something invaluable, a way to test whether the underlying principles behave as expected. One approach uses intense laser pulses propagating through specially prepared media, where changes in refractive index create regions that behave like moving distortions, effectively compressing and expanding the path that light itself travels. And in these experiments, light waves can be slowed, sped up, trapped, or released in ways that mirror the mathematics of space-time curvature, producing horizons and boundary effects eerily reminiscent of those predicted around warp bubbles. Plasma physics offers another avenue. Plasmas are extraordinarily flexible states of matter, responsive to electromagnetic fields in complex ways, and under the right conditions, density waves can propagate through plasma faster than the motion of individual particles, creating patterns that resemble superluminal structures without violating local speed limits. And I suppose that parallel should sound familiar by now. Patterns outrunning particles, geometry outrunning matter. In these systems, researchers can study how information propagates, how energy concentrates, how instabilities arise, and whether causal structure remains intact. And, while none of this moves a spaceship, it does something arguably more important. It tells us whether the warp concept is internally consistent when subjected to the messy realities of physical systems. What has emerged from this work is quietly encouraging. The analog experiments do not immediately collapse into paradox or instability. Instead, they show controlled, predictable behavior, distortions that move, interact, and dissipate according to well-defined rules. And while the scales are microscopic and the media entirely different from spacetime itself, the mathematical correspondence suggests that the warp idea is not inherently pathological. There have also been theoretical and computational studies that treat spacetime itself as a medium, exploring how tiny perturbations in energy density might produce measurable curvature effects, even at laboratory scales. These effects are unimaginably small, far beyond direct detection with current instruments. But they are not zero. And that distinction matters because physics often progresses by learning to measure what was once thought immeasurable. Some experimental proposals involve ultra-precise interferometers, devices capable of detecting minute changes in distance smaller than the width of a proton. And, these are the same kinds of instruments that have already detected gravitational waves, ripples in spacetime caused by distant black hole mergers. So the idea that spacetime distortions can be measured is no longer speculative. It has been demonstrated. If a laboratory-generated energy configuration could produce even a vanishingly small, warp-like distortion, it might leave a signature, a tiny phase shift in light, a subtle change in timing, a distortion pattern that cannot be explained by conventional effects. And while detecting such signals would be extraordinarily challenging, the mere possibility transforms the warp bubble from a metaphysical idea into an empirical target. Perhaps the most important thing about these laboratory explorations is what they do to our expectations. They ground the conversation, pulling it away from fantasies of starships and into the patient, incremental world of experimental physics. And that grounding is essential because it allows skepticism and curiosity to coexist, each tempering the other. What these experiments do not show, and this is crucial, is a flying object or a vehicle moving through space. Nothing in a lab resembles that. And any claim that we have already built a warp drive would be deeply misleading. But that is not the point. The point is that the underlying principle, the idea that effective motion can arise from structured distortions rather than propulsion, is no longer confined to equations alone. There is a kind of philosophical humility in this stage of the story, an acceptance that even if warp travel is possible in principle, it will not arrive suddenly. It will emerge slowly, piece by piece, through careful tests, refinements, failures, and revisions. And that is exactly how every major technological revolution has unfolded. The Wright brothers did not begin with transcontinental flight. They began with wind tunnels and gliders, tiny adjustments to wing curvature, careful measurements of lift and drag, and in the same way, warp physics, if it ever matures, will likely begin with obscure lab results, subtle anomalies, papers read by a handful of specialists, not dramatic launches. And yet, even at this early stage, something important has already changed. The conversation has shifted from whether warp travel violates physics to how its principles manifest in reality, and that shift is irreversible because once a concept enters the experimental domain, it acquires a different status. It becomes something that can be tested, falsified, refined, and eventually understood. There is also a deeper implication here, because if warp-like distortions can be modeled and studied, then they may leave signatures beyond the laboratory, in nature itself. The universe is vast, energetic, and full of extreme environments, black holes, neutron stars, cosmic strings, early universe phase transitions. All of these involve intense space-time curvature, and it is not unreasonable to ask whether some natural processes might produce warp-like geometries, fleeting, transient, but real. If such distortions exist, even briefly, they might leave traces, subtle patterns imprinted on radiation or space-time itself, patterns that could, in principle, be observed. And this is where the story takes on a slightly eerie tone, because it suggests that warp physics may not be something we invent, but something we discover, something the universe has been doing all along. And that realization leads naturally to the next question. If warp-like structures leave traces, what would those traces look like? How would space-time announce that it has been bent in such an unusual way? And where would we look to find the evidence? Because if the universe has ever whispered about faster-than-light effective motion, it would most likely do so not with light, but with gravity itself, in the faint tremors that ripple through space-time and reach us as gravitational waves. And so, if warp-like distortions can exist, even fleetingly, then the universe itself becomes a laboratory far larger than anything we could ever build, because space-time does not keep secrets quietly. When it is disturbed, it rings. It sends ripples outward at the speed of light. Ripples we now know how to hear. And these ripples, gravitational waves, have given us an entirely new sense with which to explore reality. Gravitational waves are not light. They do not travel through space. They are oscillations of space-time itself, stretching and squeezing distances as they pass, born from the most violent events in the cosmos, black holes colliding, neutron stars spiraling together, massive objects accelerating with such intensity that the fabric of the universe cannot remain still. And that's the thing, because if warp bubbles involve extreme localized distortions of space-time, then in principle, they too should leave a gravitational signature. This idea has prompted a quiet but growing line of inquiry, not the sensational claim that we are detecting alien spacecraft, but a far more cautious and scientific question. If a warp bubble were to form or move, what kind of gravitational wave pattern would it produce? And how would that pattern differ from those generated by natural astrophysical events? The answer, at least theoretically, is that a warp bubble would produce a very distinctive signal, unlike the chirping crescendo of merging black holes or the rhythmic waves of orbiting neutron stars. A warp-induced disturbance would have an unusual symmetry, a sharp front where space-time is compressed, a trailing region where it expands, and a propagation profile that reflects the movement of a geometric structure rather than a massive object. In simulations, these signals appear as asymmetric pulses, with frequency and amplitude characteristics that do not match any known astrophysical source. And that uniqueness is crucial, because gravitational wave astronomy is, at its core, a process of pattern recognition, of matching observed signals to predicted templates, and the more distinctive a pattern, the easier it is to identify, at least in principle. Now, it must be said very clearly, no confirmed warp signature has ever been detected, and any claim to the contrary would be irresponsible. But what is fascinating is that when scientists comb through gravitational wave data, they do occasionally find anomalies, signals that do not fit neatly into existing categories. And while most of these are eventually explained as noise, instrumental artifacts, or poorly understood astrophysical processes, a small number remain ambiguous. These unexplained signals are not evidence of warp drives, not evidence of extraterrestrial technology, but they are reminders that our universe is complex, that our catalog of cosmic phenomena is incomplete, and that space-time may still have surprises in store. And this humility is essential because it keeps speculation anchored to observation. What makes gravitational waves such a compelling avenue for this inquiry is that they are extraordinarily difficult to fake. They pass through matter almost unimpeded. They cannot be easily masked or mimicked by conventional processes, and they carry information directly about space-time curvature, not about light emission or particle interactions, and that makes them a uniquely honest messenger. If a warp bubble were ever to exist, whether engineered or natural, its interaction with space-time would be unavoidable. It would generate a gravitational footprint, a kind of wake in the fabric of the universe, and that wake would travel outward, potentially detectable across vast distances. And I suppose that possibility transforms gravitational wave detectors into something like cosmic microphones, listening not just for cataclysms, but for whispers of exotic geometry. Some researchers have gone further, asking whether advanced civilizations, if they existed, might intentionally minimize electromagnetic emissions while still producing unavoidable gravitational signatures. And while this drifts toward speculation, it is grounded in a physical truth. You can hide light, you can shield particles, but you cannot completely hide the curvature of space-time itself. Again, this is not to suggest that any detected anomaly is evidence of technology. Far from it. The scientific bar for such a claim is extraordinarily high, but the exercise itself is valuable because it forces us to sharpen our models, to understand exactly what space-time can and cannot do, and to distinguish the mundane from the extraordinary with increasing precision. There is also an intriguing temporal aspect to this search. Gravitational waves allow us to look back into the deep past, to events that occurred billions of years ago, and if warp-like distortions ever occurred naturally in the early universe, during phase transitions or exotic processes we do not yet fully understand, their signatures might still be washing over us now, faint echoes of a time when space-time itself was far more dynamic than it is today. This idea connects beautifully with what we know about the early cosmos, a period when energy densities were extreme, symmetries were breaking, and space-time was undergoing rapid changes. And, it is not unreasonable to wonder whether transient warp-like geometries could have formed then, leaving behind subtle imprints that we are only now learning how to detect. Gravitational wave astronomy is still young, its instruments improving, its sensitivity increasing, its catalog growing with each observing run. And as it matures, it will inevitably reveal phenomena we did not predict, just as every new observational window in astronomy has done before. Radio waves, X-rays, gamma rays, each opened up entirely new views of the universe. So when scientists propose looking for warp signatures in gravitational waves, they are not chasing fantasies. They are preparing for surprise, building the conceptual tools needed to recognize the unexpected when it appears. And, that is perhaps the most scientific attitude of all. What is striking is how this line of inquiry completes a kind of circle. We began with the frustration of distance. with the apparent impossibility of crossing the stars. And now we find ourselves listening to the universe itself, asking whether it has already found ways to do what we dream of, whether space-time has already explored the paths we are only beginning to imagine. And yet, even if no warp signatures are ever found, even if gravitational waves reveal nothing beyond the known astrophysical zoo, the exercise will not have been in vain, because it will have refined our understanding of space-time, energy, and causality, and it will have sharpened the boundary between what is allowed and what is forbidden. And I suppose that clarity is itself a form of progress. Still, the possibility lingers, tantalizing but disciplined, that effective faster-than-light motion, achieved not by breaking the rules but by bending them, could dramatically reshape our relationship with the cosmos, and that brings us, almost inevitably, to the human scale of this story, because if such a mode of travel were ever realized, even in a modest form, the implications would ripple outward through every aspect of civilization. Distances that once defined generations would shrink to months. Communication would no longer be a conversation with the past. Exploration would no longer be an abstract hope, and humanity's place in the universe would shift from isolated observers to active participants. And it is this transformation, this redefinition of what it means to be a spacefaring species, that now waits quietly on the horizon of our imagination, inviting us to consider not just how warp travel might be detected, but what it would mean if the stars truly became reachable within a human lifetime. And so, once we allow ourselves to imagine that effective faster-than-light travel is not forbidden, not heretical, but conditional, lawful, and geometric, the question changes again, becoming strangely human. Not how does it work, but what would it mean, because physics can open doors, but it is people who decide whether to walk through them. And this is where the abstract suddenly becomes intimate. Consider Proxima Centauri, our nearest stellar neighbor, a faint red star just over 4 light-years away, a distance that sounds modest on a cosmic scale, but one that has loomed like an insurmountable gulf for as long as we have known it existed. With conventional propulsion, even optimistic designs stretch that journey into decades or centuries, a one-way voyage into isolation. But if a warp-like geometry allowed effective travel 10 times faster than light, that distance would collapse into months, not years. A single season of human life, long enough to plan for, short enough to imagine returning from. That single change reshapes everything. Suddenly, nearby stars are no longer abstract points on a chart. They become destinations, places where missions can be conceived, launched, completed, and studied within a human lifetime. And I suppose that shift is difficult to fully appreciate, because it rewrites the emotional scale of the universe, turning eternity into itinerary. And it does not stop there, because once effective speeds exceed light by an order of magnitude, the Milky Way itself begins to feel different, no longer a sprawling impossibility 100,000 light-years across, but a navigable structure, still vast, still awe-inspiring, but no longer sealed off by time. Crossing the galaxy would take thousands of years instead of hundreds of thousands, which is still immense, of course. But now it lies within the lifespan of civilizations rather than species. That distinction matters deeply because civilizations can plan across centuries. They can build institutions, archives, infrastructures that endure. They can sustain projects longer than any individual life. And when journeys fall within that scale, exploration becomes a collective endeavor rather than a mythological one. Communication changes just as radically. Today, interstellar communication is effectively impossible beyond a certain distance. Messages crawl across space at light speed, arriving long after their context has faded. But if travel itself becomes faster than light in an effective sense, then physical presence can outpace information delay. Explorers could arrive before their own radio signals would have, and that paradoxical-sounding fact would transform exploration from a monologue into a dialogue. Imagine sending a probe, not a message in a bottle drifting for decades, but an expedition that arrives, studies, adapts, and responds in real time relative to the society that launched it. And that alone, would mark a turning point in human history, because it would mean that discovery once again unfolds within living memory. The implications for science are staggering. Planets orbiting other stars, which today are studied only through indirect measurements and faint spectra, would become worlds that can be visited, sampled, observed directly, atmospheres, breathed by instruments rather than inferred by equations, geology touched, chemistry tested, and the question of life elsewhere, which has hovered on the edge of speculation for generations, could finally be addressed empirically. And it is difficult not to linger on that thought, because the discovery of life beyond Earth would not just be a scientific milestone, it would be a philosophical one, reshaping how we understand ourselves, our origins, and our responsibilities. And if warp-like travel makes that discovery possible within a human lifetime, then the stakes of this physics extend far beyond propulsion. Exploration, however, is only one side of the story, because movement changes not just what we know, but who we are. When humanity first learned to cross oceans, cultures that had evolved in isolation suddenly encountered one another with all the creativity, conflict, and transformation that followed. And interstellar travel would be that moment, amplified beyond measure. Humanity would transition from a planetary species to something broader, a stellar species, perhaps eventually a galactic one. And that transition would challenge every assumption we hold about identity, belonging, governance, and ethics, because distance has always been one of the great separators, shaping politics and culture through isolation. And when distance shrinks, those structures are forced to adapt. There is also a quieter implication, one that speaks to survival, because a species confined to a single planet is vulnerable in ways that are difficult to ignore. Natural disasters, climate shifts, cosmic impacts, existential risks accumulate. And while space exploration alone does not solve these problems, the ability to establish self-sustaining communities beyond Earth fundamentally changes the equation. It spreads risk. It diversifies the experiment of humanity itself. Yet it would be naive to imagine this transformation as purely positive or straightforward, because the same technology that allows rapid travel also amplifies power, access, and inequality. Who decides where to go? Who gets to go? Who bears the risks? Who reaps the rewards? These questions, which already trouble us on Earth, would follow us into the stars, and physics cannot answer them for us. There is also the question of scale, because even at 10 times the speed of light, the universe remains vast. The Andromeda galaxy would still be millions of years away, the cosmic horizon still unreachable. And this is an important reminder: warp travel does not make us gods. It simply moves the boundary of the possible. The universe remains humbling, expansive, and ultimately beyond complete mastery. And perhaps that humility is essential, because it keeps wonder alive. It ensures that exploration remains an act of curiosity rather than conquest. And that balance will matter more than ever if humanity begins to move between the stars. Another subtle but profound change lies in how we perceive time itself, because if journeys that once spanned generations are compressed into months or years, then historical continuity takes on a new shape. Explorers can return, tell their stories firsthand. Knowledge accumulates rapidly, feedback loops tighten, and progress accelerates in ways that are difficult to predict. This acceleration could usher in a renaissance of science and culture, or it could strain our social structures, pushing them faster than they can adapt. And again, the physics opens the door, but it is human wisdom that determines what lies beyond it. What is striking is how this possibility reframes the earlier fears about causality and paradox. Because by respecting the speed of light locally, by bending space rather than breaking time, warp-like travel preserves the narrative coherence of the universe. History still flows forward, cause still precedes effect, and the cosmos remains a place where stories can be told and understood, and that continuity is not a technical detail, it is the foundation of meaning itself. And so, when we imagine travel at 10 times the speed of light, we are not imagining chaos or disintegration, but a subtle rearrangement of scales, a universe that is still lawful, still intelligible, but suddenly more intimate, more connected, more responsive to curiosity. Yet even as this vision unfolds, even as its implications ripple outward through science, culture, and philosophy, a final note of restraint remains, because every gain introduces new challenges, and warp travel, if it is ever realized, would not arrive fully formed and safe. It would arrive fragile, complex, and demanding extraordinary control. Stabilizing a warp bubble, navigating curved space-time, protecting travelers from accumulated radiation, managing energy flows, all of these practical concerns wait patiently at the edge of the dream, and they remind us that possibility is not the same as readiness. So this chapter, like the others before it, does not end in triumph. It ends in perspective, with the recognition that even if faster-than-light effective travel transforms our reach, it also deepens our responsibility. Because the more of the universe we can touch, the more carefully we must decide how to touch it. And that realization carries us naturally toward the final set of questions, not about whether warp travel is allowed or what it could give us, but about what still stands in the way, the technical, physical, and ethical barriers that must be understood and respected before any such journey can truly begin. And so we arrive at the final stretch of this long, winding path, not at a finish line, but at a narrow ridge where possibility and limitation walk side by side, because even if warp-like travel is allowed by physics, even if space-time can in principle be shaped to carry us across the stars, there remains a formidable landscape of challenges that cannot be wished away, only understood, respected, and slowly confronted. The first of these challenges is control, because a warp bubble is not a passive structure. It is a dynamic geometry, a living distortion of space-time that must be created, sustained, adjusted, and eventually dissolved with exquisite precision. And precision at this level is not merely a matter of good engineering, it is a matter of survival. A slight asymmetry in the curvature could destabilize the bubble, causing it to collapse or shear, and when space-time itself becomes unstable, there is no material hull strong enough to protect what lies inside. Stability is therefore not optional, it is fundamental. The warp bubble must remain smooth, continuous, and well-behaved over the entire journey, and this demands a degree of feedback and control far beyond anything we currently possess. One must imagine systems capable of sensing space-time curvature directly, not indirectly through forces or motion, but through geometry itself, responding in real time to fluctuations, correcting distortions before they grow. And that implies a level of technological sophistication that borders on the unimaginable. Then there is the problem of navigation. Because moving through curved space-time is not like steering through empty space. Paths are no longer straight lines. Coordinates lose their familiar meaning, and the destination itself may appear distorted by the geometry used to reach it. Navigating a warp bubble would require an entirely new framework for orientation, one that accounts for the fact that distances ahead are compressed, distances behind are stretched, and external reference points behave in counterintuitive ways. Even defining arrival becomes subtle, because when space-time is reshaped, the moment when the bubble dissolves must be chosen with extreme care, releasing the ship into normal space without subjecting it to violent tidal forces or bursts of accumulated energy. And this brings us to another deeply serious concern: radiation. As a warp bubble moves, it interacts with the universe around it, sweeping through interstellar space, encountering particles, photons, and fields, and while the interior of the bubble may be calm, the boundary is anything but. There are models suggesting that particles encountered at the front of the bubble could be compressed, blue-shifted, and trapped, accumulating vast amounts of energy, which would then be released forward when the bubble collapses, potentially unleashing a catastrophic burst of radiation. This is not a minor hazard, it is a central safety issue, because such a release could devastate anything in the path of arrival, including the destination itself. Protecting the ship and its surroundings from this effect would require careful management of how the bubble forms and dissipates, perhaps gradual transitions rather than abrupt ones. And once again, the need for precise control becomes paramount. There is also the question of shielding the occupants because, while the interior of the bubble may be locally flat, It is not isolated from all effects. Quantum fields, vacuum fluctuations, and boundary interactions could introduce radiation or stresses that are unfamiliar and poorly understood, and long-duration exposure to such an environment raises biological questions that cannot be answered by physics alone. Human bodies evolved under very specific conditions: gentle gravity, stable spacetime, predictable radiation backgrounds, and even subtle deviations could have long-term consequences. So the challenge is not just to move people through warped spacetime, but to ensure that they remain healthy, sane, and intact throughout the journey. Energy infrastructure remains another towering obstacle, because even reduced energy requirements are still vast, far beyond current global production, and harnessing such energy safely would require infrastructure on a planetary scale, perhaps even tapping stellar outputs directly. And building and maintaining such systems introduces political, environmental, and ethical considerations that extend far beyond physics. Who controls this infrastructure? Who has access to it? How is it safeguarded against misuse? These are not secondary questions, they are central, because any technology capable of reshaping spacetime is also, by definition, capable of reshaping power. And history teaches us that power without foresight carries grave risks. There is also the matter of reliability, because warp travel would not tolerate failure gracefully. A stalled engine can be repaired, a delayed mission can be rescheduled. But a destabilized spacetime geometry does not offer second chances, and that reality demands redundancy, resilience, and testing on a scale that makes current aerospace standards look modest. Before any crewed journey could even be contemplated, countless uncrewed tests would be required, gradually increasing scale, complexity, and duration. And each of those tests would carry risk, not just to the mission, but potentially to surrounding space, because a poorly controlled spacetime experiment could have unintended consequences that propagate outward. And yet, for all these challenges, something remarkable remains true. None of them represent a fundamental prohibition. They are not walls erected by the laws of physics. They are obstacles born of complexity, scale, and responsibility, and that distinction matters deeply because it means the universe has not said no. It has simply said, be careful. This is perhaps the most mature point of the entire journey, the recognition that the final barriers are not conceptual but practical, not metaphysical but ethical, and that places the future of warp like travel squarely in human hands, where it belongs. It also reframes our relationship with ambition, because the dream of the stars is no longer about conquest or escape. It becomes about stewardship, about learning to manipulate the deepest structures of reality without breaking them, about earning the right to travel by demonstrating understanding rather than force. And that lesson echoes far beyond propulsion. It speaks to how we approach climate, technology, intelligence, and power on Earth itself, because again and again, the universe rewards those who listen, who adapt, who move with its grain rather than against it. So the final barriers stand, tall and sobering, but not despairing. They are invitations to patience, collaboration, and humility, and perhaps that is the most profound outcome of this entire exploration, that the path to the stars does not demand that we become reckless gods, but wiser participants in a cosmos that is far older, deeper, and more subtle than we are. And as we pause here, on the threshold between what is known and what is merely possible, one truth becomes quietly clear. We do not yet know whether warp travel will ever be realized. We do not know if these challenges will yield to ingenuity or remain forever just beyond reach. But for the first time in history, the question itself has changed. It is no longer, can we break the universe to reach the stars? But can we learn enough about it to be carried by it? And that question does not close the story. It opens it outward, beyond timelines and predictions, into a future shaped not just by equations, but by the choices we make about how and why we choose to listen to the universe when it offers us a way forward. And so, standing at the far edge of this long exploration, we find ourselves in a strangely quiet place, because the conclusion is not a bang or a declaration, it is a soft realization, a reframing of how we understand limits, ambition, and our relationship with the universe itself. You see, for centuries, the speed of light felt like a locked door, a final boundary beyond which dreams of the stars would always remain dreams. But what physics has slowly revealed is something far more subtle. We were never meant to smash through that door. We were meant to walk around it. The universe did not place the speed of light there to taunt us. It placed it there to preserve coherence, to protect causality, to ensure that time has an order and that stories make sense. And once we stop treating that limit as an enemy, it transforms into a guide, pointing us toward deeper truths about space, time, and motion. Truths that are not about speed at all, but about structure. What this journey through ideas has shown us is that distance is not the simple, rigid thing we once believed it to be. It is elastic, responsive, shaped by energy and geometry, and that realization alone is revolutionary because it tells us that the universe is not a static prison, but a dynamic landscape, one that can, in principle, be traversed in ways that honor its laws rather than violate them. Warp drive in this light is not a machine, not a blueprint waiting to be built. It is a question, a profound and humbling question posed to the cosmos, asking not how fast can we go, but how does space itself behave when pushed to its limits? And that question has already paid dividends because it has forced us to confront the deepest layers of our theories, to reconcile general relativity with quantum reality, to listen more carefully to what space-time allows. And perhaps the most important shift is psychological, because for the first time, interstellar travel is no longer dismissed as outright impossible. It has moved from forbidden to fantastically difficult, and that change matters, because history is full of ideas that lived for centuries in that narrow space between impossible and impractical, waiting for understanding to catch up with imagination. We should be honest, of course. Nothing in this story guarantees that warp travel will ever become real. The energy demands may remain insurmountable. The control challenges may prove too delicate, the risks too great, and it is entirely possible that humanity will never build a bubble of space-time and ride it to another star. And accepting that possibility is part of scientific maturity. But even if warp drive never leaves the equations, it has already transformed our understanding of the universe. It has shown us that the cosmos is more flexible than we once thought, that the limits we encounter are often invitations to think differently rather than commands to stop, and that lesson extends far beyond space travel. There is a quiet beauty in realizing that the universe does not yield to force, but it does respond to insight. Black holes do not care how powerful you are, but they reveal their secrets to those who understand geometry. Quantum fields do not bend to desire, but they whisper their patterns to careful listeners, and space-time itself seems to reward humility with possibility. And so, when we say that humanity may one day move 10 times faster than light in an effective sense, what we are really saying is that we may learn to cooperate with the universe at a deeper level, to align our technologies with its structure rather than against it, and that cooperation is a theme that resonates well beyond astrophysics. Think of where we began, a species confined to a single planet, staring up at stars that seemed forever unreachable, measuring distance in light years precisely because nothing else made sense. And now, after centuries of inquiry, we find that the universe itself contains pathways we never imagined. Not shortcuts in the crude sense, but elegant detours woven into the fabric of reality. This does not diminish the vastness of the cosmos. If anything, it enhances it, because a universe that allows such possibilities is not smaller. It is richer, more intricate, more worthy of wonder, and wonder, in the end, is the engine that has always driven science forward. There is also a deeper, almost philosophical comfort here, because warp physics suggests that the universe is not hostile to curiosity. It is cautious, yes, demanding, absolutely, but not dismissive. It sets high standards. It insists on consistency, energy balance, and causality, but it does not close the door outright. It leaves it slightly ajar as if to say, if you learn enough, if you are patient enough, perhaps. And that perhaps is where humanity finds its most honest place, not as conquerors of space, not as prisoners of physics, but as students of a universe that is endlessly complex and quietly generous with its secrets. We may not be ready to travel between the stars, technologically, ethically, or culturally, but for the first time, the stars are no longer sealed behind an absolute prohibition. They are separated by challenges rather than impossibilities, and that shift changes how we dream. Because dreams constrained by impossibility wither, but dreams constrained by difficulty evolve, they become plans, research programs, collaborations spanning generations, and even if they are never fulfilled exactly as imagined, they leave behind knowledge, tools, and perspectives that enrich everything else we do. And so, perhaps the true legacy of warp drive is not that it will carry us to distant suns, but that it has already carried our thinking to a deeper place, where space is not empty, time is not absolute, and motion is not what it seems. Time, after all, is not a clock. It is a landscape we move through, shaped by gravity and energy, and space is not a void. It is a living fabric, responsive and dynamic, and when you begin to see the universe that way, you realize that travel has always been less about distance and more about understanding. We may never outrun light, and that is as it should be. Light is not a competitor. It is a messenger, a reminder of the universe's rhythm, and rather than trying to beat it, we may one day learn to let space itself carry us gently, lawfully, and with a kind of cosmic grace. Until then, the story remains unfinished, not because it has failed, but because it has matured. It has moved from fantasy to frontier, from speculation to disciplined curiosity, and that is where the most meaningful journeys begin. So when you look up at the night sky, at stars whose light has traveled for years just to reach your eyes, remember this: the universe is vast, yes, but it is not indifferent. It responds to questions asked with care, and perhaps one day, when we have learned enough to listen properly, it may allow us to step across distances that once felt eternal, not by breaking its rules, but by finally understanding them.